Hello, what's up? Today we look at LeetCode medium problem 863 all nodes distance k in binary tree. So we are given a binary tree with a root node, a target node, and an integer value k, and we need to return all the values of the nodes who has the distance k from the target. So let's say we have here this is a binary tree, the target is 5 and k is 2, so distance 2. 1, 2, this is first node on the result. 1, 2, this is second node on the result. 1, 2, this is third node on the results. So we see that we are traversing the binary tree. So if we could just get into this target node, first we need to get into this target node, and then we need to traverse in distance of 2. Let's see if we can. How could we get to this target node? Let's see the structure. So we see here that the construction of a tree node class has only childs. We don't have any parents. This means that once we get to this node, we cannot move to the parent because we don't have here any parent. Okay, this is obstacle number 1. Also, we can see that we are discussing here traversal and finding neighboring nodes. And once we start discussing traversal and finding neighboring nodes, this reminds me of a graph, because we could look at this tree as a graph. We just want to traverse. We want to get immediately to this node and traverse. And thinking of this tree as a graph, this gives us an immediate way to get to this node. We don't need to traverse this tree in order to get to this node, because in a graph, if we have an adjacency list, we can just go to the graph and tell it, get node k, get node 5. And once we get node 5, we get all the neighbors. And because we discuss neighboring nodes of this node, then this really sounds like a graph, because we discuss the neighboring nodes and also we discuss the distance. And this is two terminology items that we heavily use in graphs. So this leads us to thinking, what if we did have an arrow from 5 to 3, because we don't have. We have only arrows to the children. If we did have, then if we used BFS, we could find the nodes on distance, because in the BFS we'd first get to the neighbors. This would be level number 1, and then we would get to these neighbors, level number 2. And this is exactly what we need. So let's change this tree to a graph, or just for our sake add arrows from children to parents, and then do a BFS to get to level number 2. Okay, so this would be our method. So first I want to mention what we see here. We see level, neighbors, distance. All this really sounds like a graph. Okay, if it sounds like a graph, it walks like a graph, and it quakes like a graph, then it's probably a graph. And we see that we don't have an arrow from children to parents, which means we probably do want to add. Okay. In graph, we could describe the graph as a mapping in between a tree node to a list of tree nodes. Okay, so if we had 5, then to describe correctly this graph, we would place as the key 5 here. Okay, we would have 5 as the key, and then we would have a list of 3 to 6. Okay, this would give us the graph. Also, when we discuss graphs, we have the scene. all the items that we have already seen when we traverse it in order to find sometimes it's called scene in graph terminology. We have seen or visited, which is simply a hash set of scene. Train node. Okay. And in addition, when we go to graph to checking the distance in graph, then what we do in BFS is that we have a queue. In DFS we have a stack, and in BFS we have a queue. Basically we start from, we add this node to the queue, and see that when we use a graph, we solve this part immediately of getting to node number 5, because it's in the map. We just tell the graph, give us node number 5. No need to traverse this. And also in graph, so we have the queue. Okay, this is another part of the graph terminology for BFS. Queue. Okay, so our steps are going to be this. First, build the graph out of tree. Second, put 5 in queue of scene, in scene queue. If current distance is 0, then just return all the adjacents. Just return all nodes in adjacency to this node. If it's not 0, then current distance OK minus remove -1 is now -1, and continue the BFS traversal. Okay, so let's start coding this. First we said we want to create a graph. Okay, so let's create the graph object first. So the graph is a map, adjacency list of map of from tree node to list of tree nodes. Simply from each node we have the list of items that are next to this node. So this would be the data structure of the graph. Okay, hash map, and note that this would give us an immediate access to 5, because we just tell graph.get 5, and we have this node. So let's start building this graph. Okay, so to build this graph, let's create a sub method build graph. We're going to give it a root node. There is no parent, and the graph itself to build. So okay, so let's go here and build the actual graph. So a void static. Okay, let's go do a static. It's not static. Void build graph. It could be private. Okay, and we're going to have some node that we want to build a graph with. It's basically what this doing is for each node build the bi-directional mapping inside data structure. Okay, now node, and we need also the parent so that we can make these two arrows pairs. And this data structure of the graph that we are going to fill in. Okay, so first, if we got here nothing, then we have really nothing to do. So let's validate that we have something. Okay, so we have a node, and now we just put in the graph the node, but we don't know yet what are the other items. So we put the node array list. Okay, and now we want to add a parent. So if we have a parent, then make this bidirectional connection inside the graph. Graph.get parent, I want to add a child to it, and graph.get the child, I want to add the parent. We made this bidirectional connection, and now you can ask, but what about the other child? So what about the other child? Well, basically now we started from the root. We are going to call this method from the root. So from the root, we have no parent. Okay, so we have nothing to add, and then we want to call this one and this one recursively to create a graph. So let's continue calling this recursively. Node.left, node and graph. Okay, and build graph. Node.right, node.graph. Okay, so this should build us with the graph. So now we have the graph. We have the graph, and the graph is now stored here. Okay, now that we have the graph, we finished step number one. Step number one, build tree graph. And now we just want to traverse, let's say step number two, BFS. We simply want to do a BFS and take the distance into account. This is it. So let's make sure that we have the target. If not graph contains key target, so you see the graph gives us an immediate access. Tell you linked list to the item. Alright, now because it's BFS, we have a queue. Let's have a queue of tree node, linked list, and the visited or the scene. Set of tree node visited. This is always with the graph traversal. New hash set. Okay. Now we start by adding the target node because we want to exit from the target node. So queue.add target. Great. Visited.add target. Right. And the result. Okay. So as long as queue is empty, as long as it's empty, as long as the queue is not empty, we want to check if we reached level number 0. If we reached level number 0, return all the neighbors. Okay, so for int I 0, we need a queue size. That size. Okay, we reach level number 0, queue size, return all the neighboring nodes. Let's see, result.add queue item. Alright, and what is this result? Simply a result of integers that we had in the neighboring nodes. So we should make sure that this is a result of integers. So each item here is actually a node, so we need to take the value. What is queue item? We need to take queue item. So we actually let's just take from the queue, remove something, and get the value. Okay. So if we reached level number 0, get all the neighbors, and this is the response. If this is the response, because it's 0, so it's here, return res response. If not, we remove, we decrease the level. So we didn't do any search yet in the graph. We said if we have reached the end goal of level is 0 or distance is 0, then return all the neighbors. And see here, let's call this step number 1, step 2.1, get to the target node. And now we are going to do the traversal of the graph if k was not 0, which means we need to continue traversing the graph. So let's traverse it. Traversing the graph means we need to look at the current item in the queue and add to the queue all its friends and remove this one from the queue. Or if we're here, add all the friends to the queue and remove this one from the queue, and see, because we will already have this in scene, that we would not add it again. Great. Okay, let's do this. So we go on all over the queue that we have. Okay, and we want to add all the friends, all the neighbors. So all the neighbors are going to be a list of 3 nodes from the graph. These are all the neighbors. 3 node. See how the graph is giving us an immediate access and neighbors to all the items. Get, what do we want to get? The current item. What is the current item? This is the current item. Get it from the graph. And now get all the neighbors and add them to the queue if they are not in the scene list. Okay. So for each neighbor in neighbors, okay, check if it's in the visited. We can do this in the single command. Check if it's in the visited, and if not, add it to the visited and add it to the graph, to the queue. Okay, we check if neighbor is already in the visited. We add the neighbor to the visited, and if it's added successfully, which would mean this is true, added successfully to the visited, not already there, then we add it to the queue. Okay, and actually I think this is it, because okay, let's look at this again. So we said we want to build a graph because we want to have a bidirectional arrows. So here we build, we have graph, add to the parent the child, add to the child the parent. We do this also for the left and the right. And here we call the build graph. If there is no target in the graph, then just return something empty, and then we start the BFS. Okay, we start the BFS. This should belongs to here. For the BFS, we need a queue and the visited set. Add the first node to the queue, this one, the target, and it has been visited. And now, if we see that k is 0, meaning we are at level number 0, just return the answer, which is all the items which are currently neighboring. What are all the items which are currently neighboring? All the items which are currently in the queue. If k is not 0, decrease k, and then traverse all the neighbors. How do we traverse all the neighbors? This is why we have the graph. We tell the graph, hey graph, please give us all the neighbors of the current node that we have in the queue. And remove the node from the queue. And while you add the neighbors to the queue, make sure they were we didn't already visit them. How do we make that sure? We add a neighbor to the graph, to the visited. This would add it, and if it's already there, it would return false, so we won't add it to the queue. And then we continue with the loop. And if we reached k0, then we just return the result. Okay, looks fine. So to overall build the graph, go with the BFS, scan the graph. That's it. 2 steps. Okay, let's try it. Okay, what's the problem? Okay, something minor in line 22. Yeah, so we are missing here this larger than sign. Let's try this again. Where is this? Minus. Okay, we have here another problem. Fixed. Line 61. What's the problem? Private void build graph. We get all the parameters. Yes, I think also here we are missing this again. Cannot find sample queue size. What is the queue size? Because it's here. So the queue size, actually all of this loop should be inside, because yes, as long as the queue is not empty, then we are doing this whole traversal. Okay, so actually this whole thing is here, and actually the k is here. Yes, because we are doing this loop and this queue check only as long as we have items to scan. What's about this formatting? Okay, let's hope it's okay. Let's see. Cannot find sample, line 49. What sample it cannot find? The graphs, because it's graph. Got so many mistakes. Okay, fine. Where is this? Line 64. Yes, because I need to do a graph.put. I want to put this node. Line 70. Build graph node and the graph that I want to pass. Line 59 missing because I probably have turn. This is embarrassing. Return res, but let's continue. This is normal programming. Okay, looks good. Let's submit it. Okay, looks good. Let's go over it again. Can we see this? Okay, we started by building a graph. How do we build a graph? We tell the graph to each parent add the child, and to each child add the parent. We just want it to be bi-directional. Now that we have the graph, we do BFS. BFS has a queue and visited. Add the first node to the queue, and luckily because we already have a graph, we can add the target immediately in O1 to the graph, and then we scan it, and if k is 0, just return on the node. If k is not 0, then go to the next level with BFS. Okay, so this was it. I hope you enjoyed it, and I'll see you next time.